Today we are joined by Darrell Kuta, our Business Development Manager. With that, I would like to turn it over to Darrell.
Thank you, Sharon, and welcome everyone. Thanks for joining me today. I want to talk to you about flow measurement methods for monitoring industrial wastewater. So today the agenda is going to talk about why measure industrial wastewater, identifying applications where we can measure flow rate, primary devices that you can use for measuring your flow, and using area velocity options for flow calculations. And the two types of sensors we'll be talking about will be the wetted sensors and the non-contact area velocity sensors. So I'll go into detail on both. So industrial wastewater flow measurement, why is it needed? A lot of times it's just permit requirements or billing. Maybe you're being billed for your wastewater, and you need to confirm that you have your billing properly. You don't want to pay, because sometimes you're being billed on the influent water that's coming in, which isn't always necessarily the same amount going out. And so you may have a need to do your own self-monitoring to make sure that you're being billed properly. And that also goes into making sure you meet your compliances. Or you may need a flow meter just to verify the volume of flow. And one of the other important ones, especially for industrial wastewater, is the process optimization. And so this is basically the internal flow measurement to help determine and improve your process. So if it's like a bottling facility that utilizes a lot of water, there's going to be a big discrepancy between the amount of water coming into the facility versus what's going out. So you want to make sure that you're being billed properly based on the amount of wastewater you're sending to the effluent. I want to talk about some identifying the flow measurement locations. So if possible, you want to choose a location with uniform flow. Certain flow measurement technologies are better suited for installation locations with non-uniform flow. So we're going to discuss the differences between using the wetted AV sensors, non-contact sensors. Regardless of the technology, if it's a closed pipe or open channel, you want to make sure that you have uniform flow going through that channel to get the most accurate flow readings. And so to accomplish that, what you want to look for is the straight channel of pipe or before and after the measuring point. So you want to make sure that upstream that you're free of bends, elbows, pumps, valves. A lot of these things will have an effect on how uniform the flow is and how accurate you're going to be able to measure the velocity. And just because you do have the bends or elbows in front of your measuring point doesn't rule it out. The velocity comes into play. Slower velocity doesn't really need as much straight run of pipe in front as higher velocity, because essentially you just need time for that flow to straighten out. And so the idea is that we want minimal turbulence. And so by picking a location that does have a straight section of pipe or channel in front is going to minimize the turbulence. And so with that, I'm going to talk about some things that we need to consider. So you want to consider what are the characteristics of your flow stream. So things you want to look at are, what are the flow range that you expect to read? Does your application go from a really slow flow up to high flow, or is it always fairly consistent? What is the velocity? Depending on how fast or slow your velocity is going to determine what type of technology, or if you can use a flume or not. Because if the velocities are always over 3 foot per second, may be too fast for your flume. And then determining the size of your flume will be dependent on that flow range. And so you should work with your flume manufacturer to determine what is going to be the best size for your flow range. It's going to give you the most accuracy. Then the level is going to be a consideration. So depending on how deep your water is, if you have really low levels, less than an inch, a wetted sensor may not be the right option for you. And then it's also going to determine what size of flume you may need. And the other thing to consider is the cost and maintenance. Um, you know, is your application, does it require a lot of maintenance? If you look at it and you see there's a lot of debris buildup in there, fats, oils, and greases, you may have a lot of maintenance at that site. Other considerations are the cost of installing a primary device such as a flume. That may determine if you're going to use an area velocity sensor versus a flume. Now let's take a look at some different types of flumes. Flumes are used to calculate flow rate based on water level. So why are people using flumes? Well, quite frankly, it's they're easy to read, easy to verify by simply taking a ruler and measuring the water depth, or if you have a staff gauge, and then you look at the ISCO flow data handbook to confirm what your flow rate is. So they do make it easy to use. But you do need to determine what is your expected flow range, and that's going to help determine what type of flume that you may need. And so as far as with the partial flume, you're going to determine what your low range is, your high range is, to determine what size flume you need. Now, if the flume size is too small and you have solids going through there, that could be a problem potentially as it goes through the throat of a partial flume. Now, a Bernoullis flume, shown here on the upper left, we have some advantages of that. It's able to read low flows. You can adapt it to an existing pipe. You just cut the pipe, add some couplers on there, and install it, so it makes the installation a little bit easier. And they can handle some of the lower flows. Now, the H flume, shown here on the bottom right, they're nice because they can handle a wide range of flows. They do not need the straight run of pipe after. So if you happen to have like a drop manhole, an H flume may be a good option for you. And then the trapezoidal flume on top, they're ideal for locations where you have both low, really low flows and higher flows, because the shape of it, it narrows towards the bottom. It's able to read the really low flows, and then because it opens up, it allows you to read the higher flows. But some of the things to consider is, what is going to be the cost of installation? That Bernoullis, is fairly easy to install. Cut the pipe, install it. Whereas a partial flume, as shown here, it's fiberglass flume, could be made out of stainless steel. It's cemented in place, so there's a little bit more cost involved with installing that partial flume. Other things to consider is the approach velocity. If your application has really high velocities, and generally if it's above 3 foot per second, the flumes could actually go into supercritical flow, which would give you incorrect flow readings. But that maximum velocity, kind of depends on the flume size, but 3 foot per second is just kind of a general range that you want to look for, where it starts to go into supercritical flow. But I recommend you contact your flume manufacturer to discuss that with them more in detail. Now, all those flumes we were just looking at, they are a level to flow calculating device. And so what you can use is an ultrasonic sensor to read the water depth and then calculate the flow. Here we're showing an ultrasonic sensor. It is quite simple. It transmits a sound wave, reflects off the surface of the water. It's a function of time to detect that echo. And so it needs a certain amount of time to transmit and then receive that. It determines the distance to the surface to then calculate what your water level is. Now, all ultrasonic sensors have a deadband, and the reason for that is because it needs a certain amount of time for it to transmit, turn around, and receive that return signal. That deadband can be minimized by using like a horizontal mounting bracket that would actually take up the space of that deadband, which then allows you to have a virtual zero deadband. And I'll show you an example of that here in just a couple of slides. Other flow measurement devices, it could be radar. Radar operates in a similar fashion to the ultrasonic sensor. It transmits a radar signal, and it's a function of time to get that return signal. They do have some advantages on radar systems. The range, a typical ultrasonic range is usually 0 to 10 feet, whereas a radar, depending on the sensor, could go up to 30 feet, 100 feet. And it isn't, and they work well with different temperature gradients. Whereas a ultrasonic sensor, you should put a temperature or a sun shield over the top of it. Now a bubbler sensor, with a bubbler, you can just put an 1/8 inch stainless steel or vinyl bubble line in the bottom of your flume. It measures the amount of head pressure it takes to push a bubble out at the end of that bubble line, and then calculates the level on that. Other measurement devices are capacitance, which is essentially a couple of electrodes that are parallel electrodes, and they measure the capacitance between the sensing probes. As the water level comes up, it changes the capacitance to determine what that water level is. And last, it can be as simple as just using a ruler. Put a ruler in that flow stream, see what your water level is, and then you can look at the appropriate flow data handbook to determine what your flow rates are. Now, some things to avoid, like with an ultrasonic sensor, it would be foam or steam. The ultrasonic signal could have trouble actually trying to penetrate that. Now, as far as foam, if it's you have a lot of foam, it won't go through there. If it looks like the foam on the top of a beer, that's no problem. It should be able to read through that. But high humidity and steam, that can create problems. So what it does, it builds up condensation on the face of the ultrasonic sensor if it's facing straight down. But before I mentioned the horizontal mounting bracket, and so with this, when it's sitting horizontal, then the water droplets will then just drip off the face of that sensor instead of collecting on the face of it. With this horizontal bracket, I mentioned the 0 deadband. This allows it to transmit over here, hit the deflector plate, and go straight down. So then it gives you a virtual 0 deadband because it's able to read all the way up to the bottom. Now, other flow calculations, if you do not have a primary device such as a Flume, you can use the level sensors to do a Manning's flow calculation. So now Manning is dependent on the accuracy of the slope and roughness that you have entered in there, and it depends on free flow. It will not tell you the direction of the flow because it doesn't read velocity. And so there are some potential problems with that, is that it could overcalculate your flow if you have a surcharge or there's a blockage downstream and velocity slows down, level goes up. It looks at the level and essentially creates a level to flow table, and it looks, if the level goes up, the flow rate goes up, but that doesn't always tell you the full story. So here's an example of that. This is a 10-inch pipe that it was in surcharge, and we're using an area velocity sensor and a Manning's formula. So we can see on this top graph, the flow rates are right on top of each other. It looks fantastic, but they had an event where the pipe started to surcharge because there's a blockage downstream. Level goes up. It was a 10-inch pipe. It went up to 15 inches, but the velocity dropped. Now with an area velocity sensor, it was able to look at the level and the velocity and continue to calculate a correct flow rate. Whereas with the Manning's, that level, when it went up to 15 inches, now it's showing 225 gallon per minute for that, several hours. And then when the discharge cleared, so whatever debris was downstream, it cleared, the velocity increased because the water started to rush out of there, the level quickly dropped, and then they started to match up again. But the key is that during that surcharge, with the Manning's formula, you run the risk of overcalculating and you have no idea what happened other than your level went up. Now, using area velocity sensors for industrial flow monitoring, some things to consider is, what accuracy do you need? Do you have an existing pipe or channel? What's going to be the cost of installation? So looking at this example here, this was a fairly easy installation. They were able to cut a hole in the top of that channel. They could have put a wetted sensor in there or in the laser flow, or possibly they could have, cut that pipe out completely, put in a Bernoullis flume. So you got a couple of different options, but then it goes into the installation cost. This installation it was less expensive than trying to install a flume. And then other considerations are the maintenance. Do you have a lot of debris going through there? So you may want to consider using a non-contact sensor to read your flow rates. Now, area velocity, how does it work? So to calculate flow rate using area velocity, you need to know what the pipe size is or the geometry of it, if it's a rectangular channel or a round pipe. You need to know the water depth. When you know the water depth, you can calculate the wetted area. And then last, we need to know what the average velocity is. So when we know the level, we can calculate the cross-sectional area. We know the average velocity. Area times velocity will give us our flow rate. Now, some of the concerns for industrial wastewater that's a little bit different than municipal wastewater is that municipal wastewater, it's usually fairly consistent. It's a little bit lower in the mornings, higher in the mornings, and then lower in the evenings. But with industrial flow monitoring, you can have high velocities, low levels, high temperatures, fats, oils, greases, depending on what's going on. But let's take a close look at using a area velocity sensor. So before I mentioned that the flow rate is calculated using area times velocity, we have a pressure transducer to read the water depth. So it will read in the open channel or even in a full pipe. So it knows if it goes 100% full, the area is at 100% and times velocity to get our flow rate. So at that point, during full pipes, it's essentially almost like a magmeter where the flow rate is proportional to velocity. But with the in-pipe sensor, a wetted sensor, they send out a Doppler signal into the flow stream. It reflects off of the air bubbles and particles in that water, and it's a frequency shift to determine what the velocity is. A great thing about AV sensors is that they can read both forward and reverse flow to then calculate your flow properly. So on some applications, you could have a difficult application when you have low level and high velocity. So in-pipe wetted sensors can have a difficult time measuring when you have low level and high velocity. Similar to that picture, or that video. So the water was moving really fast, which makes it difficult to take a level reading. It's almost impossible to do a velocity profile because the water depth was only about 1 inch and 7 foot per second. So in applications like this, possibly using a non-contact sensor may be better because we're not going to disturb the flow stream, and you're able to get an accurate level reading with an ultrasonic sensor. Now, the problem with an AV putting a in-pipe wetted sensor in an application like that with that extreme high velocity is what's known as the Bernoullis principle. And what happens is as the water goes over it, it creates this down pressure or less down pressure. And so think of it as the water is ramping over there and creating almost like an air pocket underneath the water in between that sensor. And what results is a lower level reading. And then it's also difficult to read velocity because it hits the front of that sensor and just splashes all over. So if you do come across an application like that, the in-pipe wetted sensors might not be the best option. So when should a non-contact sensor be used? You can use them in most all applications, open channel flow, because they're so versatile, being able to use them on low flows, high flows, low levels, high levels. So they're the most versatile sensor. So you can use them in most applications. As we saw with that previous slide, the high velocity non-contacts work better. If you find you have an application that requires cleaning, of a wetted sensor a lot, maybe because of a low water depth and slow velocity. You know, with that combination, it's easy to get debris to get hung up on top of that sensor. So you may want to consider switching to a different type of technology. Now, the non-contact sensor, how does it work? So we have the laser flow sensor. It uses an ultrasonic sensor to read the distance to the water to then calculate the water depth and the wetted area. And then the velocity measurement, it uses a laser and it focuses just below the surface. And why just below the surface? Because we are reading the peak velocity. And when we know the peak velocity, which happens to be just below the surface of the water, then we can calculate the average. And with the laser flow sensor, we can actually do multiple points. So we can do a single point or up to 15 points at different depths and left and right across that channel. So before I'd mentioned some non-uniform flow, this is where a non-contact sensor may work better on non-uniform flow, because if I'm reading across that the surface of that water, I'm taking velocity readings from different points to get an average to then give me a proper flow reading. Let's take a look at an application with low flow. So what we're looking at here, this has velocities averaging about 5.5 foot per second or lower, levels going down to down to 1 inch. So what's happening is that if you had an in-pipe sensor, chances are you won't be able to calculate flow all the time, because of it's below the minimum specifications, whereas a non-contact sensor like the laser flow would be able to read the lower levels and velocity. Now let's take a look at a couple different applications. This particular one had very low total suspended solids. The level was down to about a ½ inch. And so at this industry, when the process system was down or the pumps were off, they had really slow flows down about 5 gallon per minute or so. And then when the pumps turned on, it went up to 300 gallon per minute. So by using a non-contact sensor, it was able to actually capture both the low flows and the higher flows. Now, other challenging applications that you may come across, like this was a fish processing facility. The customer needed to measure the amount of post-production wastewater they're discharging out to the sewer to verify their sewer cost. And so the laser flow, it provided a low-cost, low-maintenance solution that allowed them to properly read their flow, because some of the concerns was the high solids going through there, the fats, on an in-pipe sensor. They had tried a AV wetted sensor before that lasted just a couple of days before all the fats actually fouled up the sensor and made it inoperable. And so by going with a non-contact here, this allowed them more uptime. Less maintenance was needed because they didn't have to go in there and clean the sensor, and then they trying to put in a flume. The velocities were too fast on this location. So non-contact turned out to be a great option for them. Other reasons you'd use a non-contact sensor. This was a shrimp processing facility, and they needed to comply with the government regulations. They needed to measure the amount of wastewater going out to the river. And their simple solution was they were able to cut a small notch in the top of this pipe, and they were able to read the level and velocity. So it made for a very easily installation, provided them with the accurate daily flow volumes. With the flowmeter they had on there, they were also able to read the pH and temperature, and then take flow weighted samples to make sure that they were meeting their BOD compliance. Now, other industrial applications, this particular one had very high velocity. It was a corrosive material. It was a mining application. It's the tailings. And so what it looks like is like really soupy concrete flying through there. And so trying to put an in-pipe sensor in there made it very difficult. It would only last a couple hours before a wetted sensor was destroyed. And Flume just wasn't a very good option for them. So just giving you a quick look at how fast that water is moving. So this channel was about 2.5 feet wide, moving at about 8-9 foot per second. So, really a non-contact sensor was their only option for this type of industrial application. Now, other applications that you can look at this is another food processing facility, and not every application has a solution for it. This particular site, they had a lot of turbulence, high velocity, non-uniform flow. So if you look closely at this picture, you can see the water isn't even touching the bottom of the channel on the towards the top of that channel. So you need to pick your applications wisely. And in this particular site, they needed to actually just move it to a different location because because of the high solids, an in-pipe wetted sensor just wouldn't work very well. You can see there were signs of surcharging, so they just didn't have a uniform flow through there. So sometimes you just have to find a different location, or slow down the flow in this particular case, and then it started to work properly. Other applications. So if you have an existing flume, one thing you want to look at is signs of surcharge. In this case, we can see that there's a lot of debris on top of this channel, so there were signs of surcharging. And so, using a combination of a primary device, a flume, and a area velocity sensor was their best solution. So they used the partial flume for their primary flows. And then when the water level got too high and went into a surcharge, then they were able to switch over and use the area velocity sensor to calculate their flow rates. In this particular case, the suspended solids were very high, so going with a non-contact was their best option. No other applications. Again, not all applications are perfect, and so we would like to find something that has a nice straight run of pipe upstream, downstream, but we don't always get what we want. So in this particular site, you can see that it's a little challenging because we had water coming in from the top side and coming in from left to right. But what you need to do is determine what flow really needs to be read. If they need to calculate the flow on each individual pipe, you could put an AV sensor, just stuff it in that pipe as far as you can to to try to avoid that drawdown. In this case, they just use the laser flow sensor pointing downstream to capture both flow streams. They could have even improved the accuracy on the site by using a remote ultrasonic sensor over by the entrance of that pipe. But the key is you need to set your expectations, as to what flow they need to read, what are the potential problems, just make sure everyone's on board as to, the reality of that particular site. Now, as far as the data communications, most common for industrial sites is going to be an analog output or Modbus output to get your data. Most flow meter companies offer cell phones, so you can get your data, which allows you to call it up or push the data, or you can go out to the site and just manually download the data. And then last is the cloud-based data hosting, which then allows you to use a cellular modem. You don't have to worry about the analog output. You can then just push the data out to the cloud and easily view your data. So far I've been talking about just the different technologies, but other considerations are, what are you going to use as your flow meter? If it's going to be a portable meter, that runs off batteries, possibly solar panel, or if you have a AC powered site or solar power, you may want to use a more of a permanent flow meter like this signature controller with a local display. Other determining factors are if you're using an analog output, usually you want AC power because they draw a lot more power trying to send that 4 to 20 signal. So you'd use more of a permanent flow meter. So, with these controllers, there's a lot of flexibility. So you can choose, Modbus output, analog, direct download, and different sensors. So it's up to you as to how you want to build your system. In contacting your local representative, they would be happy to help you determine what's the best technology to use for your application. So some of the problems that face the industry is the data collection, and I mentioned downloading that data, which involves software. You need a place to store the data. The IT departments anymore don't like to get involved with the data storage and setting things up on your computer. So that's where using remote communications really helps free them up and you. So by using a cell phone modem on your instruments, then you can push the data out to the cloud. And we have a software program called Flowlink Cipher. And what that gives you is a dashboard view, so you can quickly look at all your sites to see, the health of your site, if they're running, battery voltage, make sure they're all up and running. It gives you that quick analysis, so you can look at the sites to see that everything is running properly. If your data is moving up and down, everything looks good. If you have flat lines, pretty quick indication that there's a problem. And you can set up alarms. So if you had, I showed some surcharge applications, you could set up alarms for if you're in a surcharge, or, the level or flow rates are too high or too low, or pH, any parameter you want, you can set up an alarm. And then with cloud-based software, it gives you access to your data anytime, anywhere. As long as you have internet access, you should be able to quickly look at your data. And the automatic updates, or the IT departments love this, because now they no longer have to get involved to update software that's on your desktop computer. If it's using cloud-based software, it automatically gets done in the background. So the Flowlink software, it's a cloud-based software, provides the complete package for most of your customer needs. You can use multiple technologies, the different sensors, either ultrasonic, radar level, bubblers, area velocity, all the different technologies and Flume devices you can use with the signature meter and send that data into Flowlink Cipher. So to recap, we need to consider, what accuracy do you need is going to determine, what type of technology you're going to use, what size flume, determine the hydraulics. The different hydraulics will determine, what type of sensor you're going to use, if it's going to be the wetted sensor, the non-contact, or possibly a flume. Do you have straight run of pipe or channel in front of that sensor? Sometimes you may have to move the location, or, just verify that you do have uniform flow. That's the key, is that you just need to make sure you have uniform flow to get accurate flow readings with any brand of flow meter. The water depth is going to be a consideration as to what flume you're going to use, or type of area velocity sensor. And the velocity, as we saw in several pictures, is that depending on the velocity is also going to determine what you're going what flow metering device you're going to use. If the velocity is too high, you might not be able to use a flume. If it's also too high, you might not be able to use a wetted sensor, so you may have to go with a non-contact. Then you need to consider your data collection. How are you going to collect your data? It's going to be analog output, manual download, send the data to the cloud. You got a lot of different options to consider. And last is the cost and maintenance. So pick your sensor or your flume, based on how much maintenance is going to be involved, and what's the cost to install it, and what's the cost for the actual maintenance. And so those are a lot of things to consider. So I recommend that you contact your local sales rep or flume manufacturer, and discuss this with them, before you purchase your flow metering device, and they would be happy to set you up with the most cost-effective and accurate system available. And so with that, I thank you for your time today. I hope you found this useful. If you have questions, as you can see on the screen, we have you can contact us through Facebook Twitter, LinkedIn, or contact us directly, and Sharon has some additional information to follow up with us.
Well, thank you, Darrell, for sharing your expertise. And as he mentioned, we're now opening this up for any questions. Please utilize the Q&A function within Zoom. And today we are lucky to be joined by Steve McManus. He is our Senior Product Support. And as Darrell mentioned, you certainly can follow us on Facebook, Twitter, and LinkedIn. We've provided the QR codes for you to scan. That way you keep up with what Teledyne ISCO is up to. So with that, Steve, I'll turn it over to you.
The first question we have here, looking for an instrument suggestion for measuring intermittent flow in a pipe. And we currently have a 720 submerged flow module in place. This would imply that we have a pressure transducer level only device collecting the flow or the non-flow, and we're utilizing some sort of level to flow relationship in the configuration of that meter to take that measured level and derive the flow rate, whether it be manning or whether there be a primary device. 720, to be honest with you, is not a complete, out of the picture option to select for that. There are other details that if we were having a phone discussion that I would ask on this, when it's flowing, what are the depths and the conditions and the state of that flow? How often is it in that flowing state versus the non-flowing state? Is there anything going on during the transition to a no flow to a flow state? Like, is there a major temperature swing? Electronics behave differently at different temperatures, and we do have temperature compensation within that sensor, but there is a lag time before it's able to keep up with and compensate for a great change in temperature. So if the ambient air temperature in that pipe, I'm just going to pull numbers out of the air here, is in the upper 50s, and when that flow turns on, it may be up in the 110 degree range. The 720 may not be the most appropriate device to select for that particular application. If we're talking a 5 or 10 degree swing, I wouldn't be as, I wouldn't even think twice about it. The depth of water in that application would have impact on it for some of the reasons that Darrell did describe in the presentation, that applications that have low depth can present measurement issues. Also, just from the standpoint of how it, the fact we have a device in the flow, if it's a low depth and there's a lot of solids and debris in that flow, we have just implemented a means to collect that debris and begin to inadvertently degrade the ability to get good flow measurement out of that particular pipe. So in that particular question, all of those characteristics have impact on what's the best appropriate technology and approach to measuring flow in that application. I would invite you to give us a call on our 800 support line, 866-298-6174, if you have specific questions that relate to that particular application that you would like to discuss with us. Next question here: how are field calibrations accommodated, and at frequency? What frequency do you recommend? For site calibration, there's only really one, parameter that is targeted for being adjusted in 99.9% of all the applications, and that's the level. When you get the sensor installed in that particular pipe, regardless, or channel, or whatever it is, what you'll need to do is you take a depth measurement of the current depth of water surface to the zero flow point. And I stress the zero flow point, not the bottom of the channel, because in certain applications, that zero flow point is elevated off of the floor of the channel. And a couple of good examples of that would be any weir, which is basically a dam in the channel, elevates that zero flow point, and that zero flow point is the depth at which it transitions from no flow to an active flow when level goes up. Another example for that would be a Bernoullis flume. The zero flow point is at an elevation above the bottom of the channel, and in the case of a Bernoullis flume, that elevation is whatever the size of the flume is divided by 6. So if we have a 6-inch Bernoullis flume, that zero level point is 1 inch above the bottom of the channel. So we would take a total depth measurement, subtract that 1 inch depth offset from that value, and then when we go to the instrument, we would dial in and tell it that the depth it is currently at is the result of that mathematical operation. There is another question here about applications that relate to situations where you have frequent low to no flow conditions. That is always a little difficult situation to deal with, simply because let's say that low depth in this case means I have a 1/4 inch of active flow in that line. Well, just from the very instance of that it's that low a depth, most any contacting measurement device is going to struggle, with maybe the exception of a bubbler level measurement. Do we have a primary device in place, a flume or a weir? If not, obviously the best alternative is an area velocity device. And again, as Darrell pointed out on a number of occasions throughout the body of the presentation, the laser flow sensor being non-contact is a very good option to choose and consider when you have an application that has very low flows. Can we use the AV sensor in a sewer invert? If used in an open-ended pipe coming into the sewer invert, what is the minimum information needed to get accurate flow data? I'll take the two-part question here, and I'll start with the first part. Can I use AV sensor in invert? Absolutely. With the asterisk there being that the transition from the pipe to the invert and to the outlet pipe is relatively smooth and doesn't have any major changes in profile. If that pipe, let's say, is a 6-inch pipe and it's elevated 7 inches off of the bottom of a rectangular invert, well, that flow is going to drop out of that pipe into the invert. It's going to have a lot of hydraulic disruption, i.e. turbulence. It's probably not going to stabilize by time it's reaching the sensor and it's in the vision of the sensor. So therefore, if that's the situation, the answer would be no. But if that transition is very smooth, in other words, the bottom of the channel that's delivering flow to the invert is at the same elevation, there's no dropout, the relative profile of the invert is close to at least the bottom half of the pipe discharging to the invert, those are going to be more conducive to good area velocity flow measurement in that particular situation. Or, as Darrell's shown in a couple of photos, if we put something like a Bernoullis flume within the invert. And Bernoullis flume is actually very suitable for that type of application if this is going to be a more permanent application where there's a great degree of desire or a high degree of provable accuracy. The Bernoullis flume and a level only measurement device would be very appropriate, as would area velocity, again, if that pipe, the invert transition is nice and smooth. Now, if using in an open-ended pipe, the first thing we want to do, and obviously the technology of choice I would consider that this is intended around is an area velocity type measurement device. We want to make sure that we get the measurement sensor far enough into that pipe that we're not being negatively impacted by the drawdown as the flow exits that pipe. As the flow exits the outlet of the pipe, the level surface will actually begin to curl down or draw down as it discharges. And if our sensor is in the vicinity of that drawdown, it's going to inaccurately measure the depth, which is, again, a very important variable that's thrown into the equation to calculate that flow rate. So we do want to get the sensor far enough up into the pipe, and the somewhat general rule of thumb is, even though it's based upon pipe diameters, really the big impact would be based upon maximum depth we expect in that pipe. So if we have a 12-inch pipe, we want to try to get that sensor 1 to 2 feet up into the pipe. But if it's a 12-inch pipe that only gets up to 4 or 5 inches, we don't need to be as far into the pipe because the drawdown is further to the exit. That's step number 1. Step number 2, therefore, becomes, once we've got the sensor installed, we need to measure the current depth of water at the sensor that's in that pipe. And then again, we adjust the meter so that it now knows that that's 3 inches or 2 inches or 5 inches or whatever the depth of water is in that pipe at the location of the sensor. And then the meter takes over and tracks the increases or decreases in depth, and it plugs in those measured depth values into the, whatever mathematical relationship we have between level, velocity, and of course to derive the flow rate. Next question here is, in my opinion, is a bubbler plausible option to measure low flow, high velocity with decent accuracy? Somewhat depends upon what we mean by those variables. What are we defining as a low flow? Or I always read low flow to mean low depth. And high velocity. If we're at a 3/4 of an inch depth moving at 5 feet per second, it's probably going to struggle. If we're at a couple of inches moving at 2 feet per second, we might be able to achieve some measure of accuracy with a level only, but we would have to utilize the Manning equation, and there are some issues with the Manning equation that do have impact on accuracy. And right out of the gate, even under the best case circumstances, Manning formula is plus or minus 20%. And there's a whole litany of criteria to achieve that degree of accuracy with the Manning equation that rarely do you find a real world scenario where you're meeting all of those points to a high degree. So accuracy with the Manning equation, it can be, kind of hit and miss. Manning's very good for trend analysis. And in other words, wanting to know if my flows, quadruple, halve or whatever throughout the day. But there could be some degree of error associated with the number just simply because of how the Manning equation is deriving that flow rate and counting on a lot of variables to be stable that may not be in that particular application. So I would be a little wary of saying, yes, high degree of accuracy. Maybe we can achieve decent accuracy, again, depending upon what numbers are being applied to this low depth, high velocity scenario. How would I measure inside a pipe if the sensor is some distance from the end? Obviously, that does create a couple of different, problems. Is it something that you have accessibility to even get up into the pipe, visibility, how far up in the pipe we are? A method of being able to measure depth in the pipe could be something as simple as, and again, let's say we've got a 12-inch pipe, just to pull a number out. If I have some means that I can maybe go up into the pipe or even at the exit of the pipe, determine the surface of the water, level at my measurement point up in the pipe, and the distance between that and the top of the pipe, I can then mathematically take my 12, which is my pipe diameter, subtract that measurement from, and in theory, I have a fairly decent level measurement that I could then utilize to calibrate the meter. You know, certain conditions like turbulence are going to maybe impact that. If there's floating debris, foam, that can negatively impact that. Maybe visibility is extremely poor and you're not able to establish where that level surface is from the outlet of the pipe. But that would be an appropriate way to at least attempt to get a calibration in the absence of being able to get up into the pipe and actually take a depth measurement that way. And then frankly, sometimes methods of making that depth measurement themselves, sticking a ruler in the pipe, even in an open channel, you get the water rides up a little bit on the ruler. The surface of the water may be bouncing up and down. You may have parallax error, whereas the ruler is not 100% perpendicular, straight vertical. It might be leaning one way or the other, and that's going to induce some degree of error. Visibility may be poor, so you're not able to see the little markations on the ruler itself to be able to establish what that level is. So taking a depth measurement in an active flow can be, have some sources of error. One other thing that we could consider, and again, this depends upon what type of sensor we're utilizing. If we're using a 2150 sensor or a 350 sensor, both of which are contacting AV sensors, because of the method that they are calibrated at the factory for instrument calibration, their zero level point is calibrated in effect, open air. So you can orient the sensor properly in open air. In other words, you have the top of the sensor up, the bottom of the sensor down, because that transducer is quite sensitive. And if you have the sensor rotated to where it's upside down, gravity pulling on the diaphragm of the sensor will induce a little bit of bias. So if you have that sensor physically oriented top up, bottom down in open air, and adjust the level to 0, and then install it in the pipe and ensure that you get the sensor as close to the 6 o'clock position in that pipe as you can, that is a very reliable and very accurate method of calibration for that specific sensor type. And that's all of the questions that have been submitted at this point in time. I'll stall around and stumble and give somebody some options here to add additional question if they come to your mind. But once again, I just want to state that if any questions do pop up, you have Sharon's email. You can forward any of those questions to her, and she will in turn forward them on to me. I would be happy to answer any questions that pop into your head after we're done here, whether that be later this afternoon, tomorrow, or next week. I also want to take a moment to, again, thank you for taking the time out of your busy days to spend with us. We do truly appreciate you being with us here today. And with that, I think I'll go ahead and we'll close the question and answer session. And everybody, please have a great day.